All right, so here we have our exponential function. Again, if we start with our intercepts, plugging in 0 for x, what do we find? Our y-intercept is equal to 0. Which basically tells us 0, 0. That one was easy. To find out our x-intercept, well, can you see that 0, 0 will also be an x-intercept? But if we solve for our x-intercept by making y equal to 0, there's some important things that happen. First of all, we're going to check the following. This is multiplied, so either x could equal 0, which we already knew, or e to the x could equal 0. Is e to the x ever equal to 0? No. One way to think of that is you can have the image of the graph. What do exponential functions look like? What does the graph of e to the x look like? It looks like this. It's always increasing. Some of the points you might remember from graphing it. When the exponent is 0, anything to the exponent 0 is equal to 1. If the exponent were 1, and you plug that in, you would get just e. This is the graph of e to the x. From your previous years of studying that graph, you might have remembered it has an asymptote at y equals 0. It never equals 0. So when looking at the x-intercepts here, we do get x equals 0 as one possibility. This one never equals 0. And that's going to come up over and over again in this question when we do our derivative and our second derivative again. So that's a key concept. For the asymptotes on this one, what happens as x gets really, really big or really, really small? This one's a complicated one. Okay? We're gonna rely on our graphing calculator to look at asymptotes on this one, because this one, the limit as x goes to infinity of 2x e to the x, does it make sense that 2x gets really, really big? E to the x gets really, really big. This is going to be infinity. Right, title asymptotes. If we look at the limit as x goes to a really big negative number, this is where we get an issue. What happens as x gets a really big negative number? 2 to the x. I'm just going to put it in brackets underneath. Can you see that that's going to get to be a really, really big negative number? But what happens to e to the x as x goes to negative infinity? Look at your graph. As you go this way, what does it get close to? It gets close to 0. And this is where mathematics has some issues. What's 0 times negative infinity? 0? Or negative infinity? Because they're both getting close. We're either getting close to a really, really big number and we're getting close to 0. It just depends which is getting bigger or smaller faster. And that's the part that gets complicated. There's going to be some times in mathematics when you do 0 times infinity that it's equal to infinity. And sometimes in mathematics when you do 0 times infinity and it's equal to 0. We're going to find out what's going to happen in this situation with our graphing calculator after we've done a little bit more. So we're going to leave this for now. And we're going to look and find our stationary points and our inflection points. So for finding our stationary points and inflection points, again, we'll do our derivative. Our derivative this time is going to have a product rule because we have 2x times by e to the x. So we need to keep one of them the same. So let's say I keep 2x the same and do the derivative of the other one. What's the derivative of e to the x? E to the x. And now I'm going to keep the e to the x the same and do the derivative of 2x. And the derivative of 2x is just 2. Before I set this equal to 0, I notice that there's an e to the x in common in both of these. I'm going to factor that out. And now that I set it equal to 0, again, we talked about this before, this part is never 0. But this part would equal 0 if x were equal to -1. So -1 is going to be the only critical point as far as finding out whether that is a maximum or minimum. Okay? We're going to need to plug in some values. Some other things about e to the x. Not only is it never equal to 0, but if we look at what property does e to the x have, it's always positive. So it's never equal to 0 and always positive. So now, when I'm plugging any number into here, it's only going to be this part here that's going to affect whether it's positive or negative. So if I plug a number less than -1, like -10, can you see that this section is going to be negative? This section is always positive. So we know our function is decreasing before -1. After -1, it's going to be positive, so it's increasing after -1. For our second derivative, two different ways you could go about your second derivative. You could either use the factored place and then do the product law with that, or you could use the expanded one and do product law with this part and then do the derivative of this as well. So either way, it's going to be fine. We're going to simplify it afterwards as well. I'm going to use the one that's already factored. So keep one of them the same. So if I keep e to the x the same, the derivative of 2x plus 2 is just 2. And if I keep the 2x plus 2 to the same, the derivative of e to the x is e to the x. Again, you can see that you can factor out an e to the x, leaving you with 2 plus 2x plus 2, which will be 2x plus 4. Set that equal to 0. Again, e to the x is never equal to 0 and always positive. So the only place it could equal 0 is at -2. And the only thing that's going to change whether it's positive or negative is that 2x plus 4. So plug in a number less than -2, and this will be negative, meaning this section is concave down. Plug in a number bigger than -2, and this section will be positive. meaning this is concave up. So what do we have? We found out that at -1 we have a local minimum, and we found out at -2 we have an inflection point. So if we want to write out the coordinates of those points, -1 comma something is going to be a local minimum, and -2 comma something is going to be an inflection point. How do we find the y-coordinate of a point? This is on our actual graph. We plug it back into our original equation. So when I plug it back into my original equation, I'm going to get -2 e to the -1. If this was a non-calculator, that's as much as you could do. If it was a calculator question, we'd actually plug that into our calculator to see what that's equal to. -0.736 rounded. Same thing when you plug in -2 into your original equation. If you didn't have a calculator, the best you could do is -4 e to the -2. If you plug that into your calculator, you get -5.41. -0.541, sorry. So what do we have? We know that our x and y intercept point was 0, 0. We know we have a local minimum, and just based on the values that I have here, I'm going to make -1 right there. At -1, -0.0736. That'll be 1 point, and I know that I have an inflection point at -2, -5.41. So that inflection point at -0.541 will go right there. Yeah, this looks pretty, doesn't it? Sorry. Here we go. -1, here it is right up here, -0.736. I'll rewrite this one too. So what do we know? We know that it's increasing after -1. We know that it's decreasing before -1. We know that it's concave up before -2. I mean concave down before -2 and concave up afterwards. Now I'm going to go back to our asymptotes, because what I said before is one of the things we notice is when x goes to big numbers, it goes up to big numbers. So as far as what that tells me for my graph is I know that in this section that's concave up, it's getting bigger and bigger and bigger. So I can draw it like this as a sketch. When I look at my limit as x goes to -infinity, at what's going to be happening when x goes to -infinity? We had two options, because I said we have -infinity times 0. Sometimes that's going to equal -infinity. Sometimes that's going to equal 0. Some things to analyze here. First of all, e to the x is always positive. So when we go to negative infinity, this is always going to be a negative number. Does that make sense? And if that limit approaches 0, it's going to approach 0 from the negative side. Or if it goes to negative infinity, it's going to go down to negative infinity. It can't ever go to be a positive big number. So now let's look at the two options that we sort of discussed. One of the options is it's equal to 0. The other option is it's equal to negative infinity. If we go back to our graph, it's concave down. So I'll draw both options. One option is it goes down to negative infinity. The other option is it approaches 0. We could plug in a point. We could plug in a very large point and see what it gets close to. Like we could plug in x is negative 1,000 and see, does it come out to a big number or does it come out closer to 0? And that would really help us. But the other thing about calculus is I know that it can't be this. Because if it is that, what would I have found? I would have found another maximum. But I didn't find another maximum point. And I also know from my first derivative test that it always has to be decreasing. So if it would go back down to negative infinity, there would have to be a place where it was increasing again. So the calculus is going to tell me that it's the only way that it can keep decreasing but stay negative is if there was sort of a half asymptote, because it only affects the left side of my graph at y equals 0. Now, since this question would have required that you use calculator to get decimal values of those points to get an idea, to graph it anyways, then you would have your graphing calculator and you could plug in big numbers for x like negative 1,000 and see what happens. So if I just type that into my calculator. Two times negative 1,000 at 1,000 already, it says it's so close to 0 on my calculator that it's equal to 0. It's already got so close to 0 that it won't even round anymore. Now technically it's not perfectly 0, but it would be really close to 0. So we do have a partial asymptote at that point. It's technically not wrong to draw that asymptote all the way through, because an asymptote, when it's drawn, is just part of the graph to tell you what your graph is going to behave like. And for horizontal asymptotes, it can happen that a graph goes through a horizontal asymptote at the middle, because horizontal asymptotes are telling you what's happening at the extremes, either as x goes to negative infinity or x goes to infinity. And so for this one, as x goes to negative infinity, our graph gets closer and closer to 0.